So we have different absorption energies. We have different colors. How do we put this together in terms of a general rule that we're going to analyze in a textbook? So that leads us to the next topic, which is called the Spectrochemical Series. So what we can say about this is that ligands can be arranged in order of their ability to increase delta, which is the energy gap between d orbitals and what we call this is, or chemists refer to this order as the spectrochemical series. So the spectrochemical series is this big long list of various ligands. It starts on one end with Cl minus, followed by F minus. And when we write out the spectrochemical series, we list a ligand and use a greater than sign to show that, in this case, the fluoride ligand would have a larger crystal field splitting energy than a chloride ligand. If they were in an octahedral environment, that would mean delta O for F minus is going to be greater than delta O for Cl minus. We can then include a long list of the ligands. So the next one in line is water. Ammonia is going to be greater than water, which we saw in the previous example. Next is ethylene diamine, which is abbreviated EN, which we talked about as a bidentate ligand, followed by NO2, and lastly CO or CN minus. These are the common ligands that your textbook lists. There's in reality a large amount of ligands that we can analyze, and typically when you see this chart, it's drawn with an arrow and it says increasing delta. So this is going to increase the delta for whatever complex that these ligands will bind to. On the left-hand side over here, we refer to these ligands as weak field ligands. And over here, the COCN case, we refer to these as strong field ligands. So this enables us to start to analyze complexes in a little different way. The example that I gave to start this analysis was a D3 complex. And a D3 complex in an octahedral environment is kind of easy to analyze because there's only one possible electron configuration that could arise from that. But if we have something like a D4 case, we can kind of see two scenarios could potentially exist. So if we have our energy scale and we show the splitting between the T2G and the EG orbitals, if we have 3 electrons, there's only really one feasible electron configuration that would work, and that would be something like this, where all 3 of these electrons are spin up in the lowest energy case possible. But what happens if we have 4 electrons? We actually end up seeing 2 scenarios, because the first scenario would be to take the first 3 electrons and fill them into the T2G orbital. But the question is, where would we put the 4th electron? One scenario would be to put the 4th electron up here in the EG orbital. The second scenario would be to fill up the T2G orbital with its 3 electrons, and then put the 4th electron down here. So the question is, which case will the electron choose to go with? Would it be number 1, where it goes in the EG orbital, or would it be case number 2, where we have a T2G, 4 electrons in the T2G orbital? One thing that we can definitely say for sure in every instance is that the electrons will fill the orbitals to attain the lowest energy electron configuration. That's going to happen in every single case. The question we need to then ask ourselves is, which case do we have, the one on the left or the one on the right, that will give us the lowest energy configuration? And this is going to change based on the nature of the transition metal or the nature of the ligand. So let's kind of take a step back for a second and ask ourselves, what is giving us this energy, or how can we relate energy to each of these 2 electron configurations? In the first case, we're going to put these 3 electrons down here in the T2G orbital. So that's going to be like our baseline, because in each case, there's 3 electrons in the T2G orbital. We can assume that that's going to be the lower energy electron configuration. Okay? So what's the difference in energy, or what I'll call the energy cost, for each of these 2 scenarios? Or how much more energy do you have to put that 4th electron in here? For scenario number 1, the energy cost would be equal to delta O, right? Because we have an octahedral complex. This is delta O. By putting this 4th electron up here in the EG orbital, it's going to cost energy, so our energy cost is delta O. In the second case, remember that electrons have, when we put 2 electrons in the same spot, there's going to be an electron-electron repulsion. These electrons will do anything they can in their power to get to a lower energy configuration. In this case, we definitely know that if I put 2 electrons in the same spot, they don't want to be there, and they want to minimize that repulsion. So they start to do this little electron dance, which is really one electron spinning one way and the other electron spinning the other way. They do that to minimize the repulsion as much as they can. But in this second case, we have an electron-electron repulsion, which we call the spin pairing energy. So there's the cost that's associated with putting that electron there is something called a spin pairing energy. And because of this, and because of these 2 situations that arise, we kind of have to give a name for each one. And the name that we're going to give is a high spin complex versus a low spin complex. So scenario number 1 we refer to as high spin. And scenario number 2 we refer to as low spin. And the reason we use this nomenclature is for the following. If you remember back to chapter 6 of the textbook, in chapter 6 we talked about sets of quantum numbers to describe each of our electrons. And there's a bunch of quantum numbers, but the very last one was the spin quantum number. And we either gave an electron a value of +1/2 or -1/2 based on what direction that spin is in. In scenario number 1 over here, we have 4 electrons that are all spin up, or we have 4 times +1/2. So this is going to give us an overall spin of +2. In the low spin case, if we look at each of these electrons, 3 electrons have a +1/2 spin, and 1 electron has a negative 1/2 spin. So our overall spin here is going to be +1. This is why we call one case high spin and another case low spin. When we talk about spin moments of electrons, this is where the magnetism part comes into play. And we can have electrons in case number 1, we have 4 unpaired electrons, and in case number 2, we only have 2 unpaired electrons. So their behavior when they're introduced to a magnetic field is going to be slightly different. So the question is, in this case, when do we observe high spin and when do we observe low spin? This is going to depend on the geometry, as we're going to find out in a couple minutes for a couple other geometries. But what we can say is that for an octahedral complex, a strong field ligand and a 4D, 5D transition metal always give low spin. I should say a strong field ligand or a 4D or 5D transition metal will give low spin, because both of these don't have to be present. It's either one or the other. If there's a 4D transition metal in the center, we'll have low spin, even if it has all weak field ligands. If there's a 3D transition metal that has strong field ligands around it, you're going to get a low spin environment.